It's the September meeting of the Central Arkansas Astronomical Society. And we're, of course, meeting virtually because it's not prudent for us all to climb into that classroom out at the River Ridge Observatory. The observatory is open, and we've got some pretty clear common sense rules for staying safe out there. We have plenty of room for people to observe. If you're new to the club, just let somebody know if you need an orientation, and we'll help you out. And we should enjoy the site that the club owns. I'll just go right into the presentations then. We have two tonight. We have Bruce McMath, who's going to talk about the globe at night. And then Dr. Jeff Robertson is going to talk about the cosmic distance scale. So Bruce, if you're ready, have at it.
I've got 3 web pages I want to share with you all that deal with light pollution. We don't normally deal with light pollution in our club programming. I think we're about trying to get around light pollution, not address it. And so I think I've given one presentation at a club meeting on the topic and that I can remember. We often have programs at our public events, but not club meetings. And one reason is that my sense is that most people get are fatigued with worrying about trying to figure out how to get around it, and don't really want to hear about how to address it. And I think that leads to a certain fatalism in the astronomy community among many people. They don't seem to get. It's a surprise to me that more people don't get involved. And I think it is from that phenomena that if you spend all you can't, we're not going to improve light pollution between now and the next clear night. So there's no sense in worrying about that. You try to deal with get a camera or filters or whatever, and a certain fatalism sets in. It seems like in ANSA, for example, more than half our steering committee members are not sky watchers at all. They're people with an environmental and naturalist bent that seem to really, for the most part, disproportionately anyway, invest in it. But I've got these 3 websites. I want to run 2 of them real quick, and then the fun one, and some of you may be familiar with it, is the globe at night. But unless you've delved into it, which I was aware of it for a long time, but I never got into it till I had to present on it the other night. And I began to realize how much is there and how much fun it can be to participate in that program. But first, 2 quick ones, which are going to be my lecture, so to speak. And one is ANSA's website under how you can help. There is a You and Nature at Night page. And I would encourage all club members to take a few minutes to go there and look at it and explore what all is mentioned there. But at a minimum, do these things that are listed as things that anyone who visits the page really ought to do. One is to join, or follow rather, ANSA's Facebook page. We have a new Facebook page. That's not our group page. Join our group page, as you can see right here, and then go here and certify your home. It'll cost you nothing, and it won't take much time. You can go to this web page right here and go through a simple process to judge your own home lighting. And it's a little checklist, and then make any changes you need to make, and then you can self-certify yourself. And then if you do this, go and post the little graph. You can download the certificate and go and post that on our group page. I'm trying to get people to not only do this, but then to share that they've done it. So those 2 pages right there, the self-certify IDA home certification responsible lighting page, and ANSA's You and Nature at Night page. So let's get down to where I really wanted to go. uh, which is the citizen science project, Globe at Night. Now, how did that not happen? All right, let me just do it this way. I've got a bad link there. So this is the Globe at Night web page. Now, this has scientific value. It's a citizen science project, and you can turn in data on your sky or any place you go to observe or where you live. It's not important that it be a dark sky place and spot. In fact, it's just as important to be where you live. That's really what they're trying to do, is document the sky everywhere. And these are the people, or at least let's put it this way, the people who create that light pollution map that you find online, that they have generated with using satellite imagery. But to make that work, they have to calibrate it. And so they need visual, and you can continue with using meters and things. But right now, this year in particular, they're trying to get people to go out and do visual assessments of the light pollution in various places, of course, around the world. And the purpose of this is to recalibrate, and they're having to recalibrate. They did this once, but with the lighting technology changes, the spectrum of these new LED lights are different from the high pressure sodium and the mercury vapor that preceded them. So they're concerned that they need to reestablish the calibration. And so they want people to go and out and particularly this year and do this. Now, it's easy to report your findings. There's a web app that you go to, and it automates some of it, like your location, or you can plug in your location. It's just a simple 4 or 5 step process that you can do online over your cell phone or your iPad or your computer. And then you make some notes and you turn it in, and you can register this. You can get lined up to do this and have it count toward as a citizen science project if you want to, or you can just turn the data in. And when you do, it'll show up. Let's see. It'll show up on this map right here. So we can go to full data set maps 2019. It's taking a while to load. Here we go. And zoom in. And your data, and everyone else's for that matter, will show up on this map. Which is, as I say, taking a minute to load. So you can go up here where our observatory is. You can see these up here. Jeff, somebody in your neck of the woods has been doing a lot of this, because look at the cluster around Russellville. I've not noticed that before. But you go in here and you can see this was an SQM reading probably that I made with a meter, not an eyeball reading. So how does this work? And this is where it gets fun. The way this works is they've got this set up. So this is 2020. We're in the Northern Hemisphere. So we go down here to September, and they tell us that we should use Cygnus between September 9 and 18. Now, obviously, they've picked these periods out because they're moonless periods during each month. And they've picked out usually 2 constellations to use, but you only need 1. And they actually give you a little map of the sky that surrounds Cygnus. You can put in your latitude here to adjust that, and then you can get over here and read the mythology of Cygnus, each of these constellations. So this is particularly if you're a new observer, there's double value to doing this, because you're going to learn the constellations, the major constellations, as you are getting your data. And so what you do is you go out and you use these charts, and they're in 1 magnitude steps, which seems sort of crude, but apparently they're able to make this work. You get enough data from enough people, you can statistically work this thing out. So here are different 1 magnitude steps of Cygnus, and you can practice this. On this page, it gives you the option to practice this. So here we've got, well, this is for Orion. Let me go back. Should be able to practice. Well, let's just go do Orion. Let me get Orion up here, if it's going to default to Orion. If it'll let me do it. Doggone, it's not going to let me do it. Yeah. All right. Now the magnitude charts for Orion. Practice observing. So here's a practice chart, and you select what you think this is. First magnitude, second magnitude, third magnitude, etc. So let's go back. Let's look at this, and we can see that we're seeing all the belt stars, and we're seeing a bunch of stars in the shield. And by the way, this is a great way when you're doing your observing and you're being asked what the clarity or transparency of your sky, using these charts can at least get you a bracket. You know, a lot of people talk about using the Little Dipper, but the problem with the Little Dipper is that it's often not anywhere near the zenith. So it's not a very practical way of doing it, of checking your magnitude limit, unless it's fairly high in the sky. So at any rate, we go back here and we can see a 4th magnitude chart. Oh, what happened? Oh, okay. I'm not seeing as many stars in the shield as we were seeing in the sky a while ago. This looks more like it, 5th magnitude. So we can go back here to our chart, and we can practice, and we'll select 5. And I've done this before, so I know it's right. Select 5 and submit. That's not quite it. Oh, they changed it on me. Please try again. Refer to the outline and print a magnitude chart if needed. All right. Well.
No, you got it right, Bruce. They gave you a new one.
Oh, they gave me a new chart. Yeah. There we go. I see. So anyway, that is Globe at Night. It's, as I say, a citizen science program. You're going to go out. Why not take a minute, step outside your house on a clear night, for that matter, or go down to a nearby park, or when you're out observing. Just put this in your list of things to do. It just take a few minutes, and it'll get you started on your transparency reading. You can check up on mythology here, and then you can make a contribution to the International Light Pollution Map and that important process of data. Now, one more thing I wanted to say and forgot to say, and that is I mentioned that sometimes I think that astronomers don't get involved because they're fatalistic. They're resigned to there being nothing that you can practically do. But the truth of the matter is, I mean, that's not the case. Things are happening. Progress is taking place. And I've got just a few things here I want to show you that can demonstrate how we are making some progress in fighting the problem. This is the, believe it or not, the Searcy County Chamber of Commerce's a cover of their annual banquet this last summer, this year, this current year. The stars are always out in Searcy County. The whole program, the keynote, was about their dark sky asset and the dark sky and the value of it in their tourism industry. They are really pushing the tourism, dark sky tourism in Searcy County. And then you see things like this. This is a ballpark in Springdale, Arkansas. Beautifully zero up light illumination. And if you pay attention, you'll notice that the highway lights, all our highway lights, when the old gooseneck fixtures have to be replaced, zero up light fixtures are going in. So we're making some progress. And then even individuals, and I don't even know where I got this picture. I think it was from our group, Facebook group page. But even individuals are starting to respond in the way they like. So it's not a lost cause. It's a slow process, and I would encourage you to go to our ANSA page that I pointed out at the very beginning and go through that checklist and then participate in Globe at Night. That's all I got.
Well, thank you, Bruce, and we should all try that out and add to the information that's available on light pollution and the analysis of that. The next, well, are there any questions for Bruce?
Where will we find these links that he just pointed out?
All of those links are on that darkskyarkansas.org. Darkskyarkansas.org is the ANSA's website, and under how you can help is that first page I showed you, you and the night sky environment, and that's got everything on it. You can find
Thanks, that's a good job. Thank you.
Everything I've talked about.
All right, our next presenter is Dr. Jeff Robertson, and he's going to talk about the cosmic distance scale.
All right. Well, welcome everybody. What a cool, I was unaware at the Globe at Night app thing. What a cool way to learn constellations and then participate in citizen science. That's really awesome. So I'm going to share I guess I'll share my screen. All right, does everybody see my PowerPoint?
Yes, it's showing.
Yeah.
All right, well, here we go. So I'm going to talk a little bit about the cosmic distance ladder. How do we understand distances in astronomy? And this picture is the Hubble Deep Field. And it's just hard to imagine the scale and vastness of our universe. This image here is taken by the Hubble Space Telescope in a part of the sky that covers about the size of a dime, seen 75 feet away. And this mosaic is about 342 separate exposures. More than 100 hours of time with the Hubble Space Telescope pointed in one of the most empty parts of the sky they could find. Can you imagine that observing proposal. We'd like to point the HST at nothing for 100 hours. You can think of the people going, what? What a waste of time. But there are about 3, maybe 4 stars in this image in our galaxy, but every other single thing in this image is a galaxy outside of our own. So nearly every object you see is a galaxy. And again, this is pointing at the most desolate, empty part of the sky, the size of a dime at 75 meters. So the sky is filled with galaxies. So an appreciation of vast distances encountered in astronomy can be seen in a great video resource. It's an oldie but a goodie. And if you have not seen The Powers of 10, it's a short 9-minute video that is really cool. It starts by looking at these people on a blanket at the lakefront outside of Chicago, and it starts expanding outward in multiples of 10, and it zooms out to the farthest reaches of outer space and then zooms back in towards the person into an atom inside their hand. And so it's a wonderful video, and if you haven't seen the video, you kind of need to understand the cartoon, but once you've seen the video, I encourage you to do that. You'll laugh at the cartoon anyway. It's a great example of the vast distances encountered in astronomy. So the easiest way in which to determine distance is the fact that a common tape measure won't do, but if a tape measure would do, I'd like to volunteer because I'd like to measure those distances and go. So we use the speed of light, and an Apollo astronaut stuck some retroreflectors on the moon, and here's a picture of them sticking their retroreflectors, and we shine lasers from the Earth, and they bounce back off the retroreflectors, and the light travel time there and back, distance equals velocity times time, or the velocity is the speed of light, gives us very accurate distances to places where we're flying around in the solar system. The first rung on the so-called cosmic distance ladder involves a geometric method of determining parallax. And the easiest and best way for everybody to understand parallax, and those of you with video, I'm going to watch to make sure you're doing it. Your homework assignment is right now, in the next 30 seconds, follow me. You put your thumb up at arm's length, and you alternate looking at your thumb with your left eye and your right eye. And your thumb will appear to move against the background that's much further away, depending on how close your thumb is to your eyeball. And you can practice doing that by blinking your eyes and looking. But basically what you're simulating is your eyeballs represent the Earth 6 months apart in its orbit around the sun. And your thumb represents a star or something that you're interested in and figuring out how far something away is. So that shift that you see in your thumb is the angle that is being created because you're looking at it from 2 different sides of the orbit or your 2 eyes. And you'll notice that if your thumb is very far away, it shifts very little, but when it's really close, it shifts a lot. And so that angle depends on the distance, and it's a geometric way of determining distances. With our instruments in the orbit of the Earth, we can measure parallax shifts that give an accurate distance out to stars nearly 3,200 light years. So within 250 light years of Earth, there are over 250,000 stars. So that's very cool. I've got a website, a series of websites on the very last slide that I'll leave up for a while, but one of them is an atlas of the universe that has a map of all the stars within 5,000 light years of Earth. And this is an example of parallax looking at the background stars and the closer stars as the Earth rotates around the sun. And you can see the shifting of some of the stars that are nearby relative to the stars that are much further away that don't appear to shift very much as the Earth orbits around the sun. And we get that look from 2 different sides of the Earth's orbit. And that was so fun. We should play that again now that you know what you're looking at. So now let's think about that. We now have a catalog of 500,000 stars that have measurable parallaxes that we know the absolute distances to. And now that we have that parallax catalog with very accurate distances going out about 3,000 light years, we start to note some common features of these stars, and we begin to categorize them based on their common characteristics. And one of the ways we look at stars is to pass the light through a prism and look at the spectrum, the rainbow of colors from their light. And an example is shown here for a lot of different stars. Each little colored band is a spectrum, the example of taking the starlight and passing it through a prism. And you can see that all stars are not the same. They have different spectral lines. They have different, some of them have stronger lines in various colors, and others have different lines in other colors. And there's a sequence of stars. And so we begin to categorize all those stars of known distances based on what they look like. Now, it turns out that these classes of stars are actually, they have something to do with their surface temperature. Originally, I think they categorized the stars based on the strength of the hydrogen lines, and they came up with A, B, C, D, E, F, G, and etc. And then once they learned that, oh, it's actually temperatures, and then they organized them in terms of temperature, now we got this crazy scheme where it starts off with O, B, A, F, G, K, M, and I don't know what happened to all the other letters, but anyway, that's the sequencing of stars based on their spectral type. But you can imagine it's a lot like sorting the stars into certain light bulb wattages or something like that. So a really famous diagram in astronomy involves looking at the light of a star versus its temperature, or alternatively its spectral class. What kind of light bulb is it? And the HR diagram is very useful because we use the stars that we have known distances to, so we know how intrinsically bright they are. And if they appear fainter than we think they should be, it's just because they're further away. If they're brighter, they're closer to us. But if you know their absolute, if you know what their wattage is, so to speak, and you know their temperature, you can place a star on this HR diagram. And you can see stars inhabit different areas on the HR diagram. So the y-axis again is brightness, and the x-axis is the temperature of a star. This section of stars along here, this long line, are called main sequence stars. You can see that most stars in this diagram inhabit this area. And these are all stars that are sort of adult stars that are burning hydrogen into helium in their cores and have, they're sort of in the mid-time of their life cycle. Stars are a lot like people. We have toddler stars, and we have young adult stars, and then stars when they're adults from 18 to, I don't know, 60, spend a lot of time on their main sequence, and then they spend a lot of their life in other parts of the HR diagram when they're undergoing drastic changes like adolescence or receiving their first AARP card. This is a more complex HR diagram that it's kind of fun to show because it has a lot of the names of the stars on it, if you can read them. So stars like, let's see, up here to the right, you can see Antares and Betelgeuse. And down here somewhere, you can see right in the center, the little yellow star, the sun. And what else we got? Sirius is over here, a little star over here. And so you can kind of see where they are on the HR diagram. So combining the information about stellar masses from, say, looking at binary stars that are only obtainable from eclipses with the temperature and brightness will yield information about the stars and their masses and sizes and densities relative to where they fall in this HR diagram. So because we have absolute distances, and from binary stars we know their masses and radii, we can begin to really tell something interesting about the stars and know how bright they are and what they're doing, what their actual size is. All right, so now consider a cluster of stars at some distance that are much too far away to have any observed parallax. So in terms of your thumb, they're not even at the back of your yard. They're like 1,500 miles away. Well, your thumb's not going to move any, so parallax is not going to be useful for determining distances across those types of stars. But we can observe the spectrum. We can pass the light through a prism and look at the spectrum and categorize it based on those spectral classes and get an idea of what wattage light bulb it is. So this allows a different type of HR diagram to be constructed, one that plots brightness versus the spectral type, not absolute brightness, but how bright it looks just because we're seeing it from Earth. So this is for the Hades cluster. And this is just a Hubble Space Telescope image of a really cool region of the sky that has a lot of gas and dust where stars are being born. Here's a brand new cluster that has emerged. Here's a star that is either blasting off a lot of energy, or this is a supernova remnant ring or something like that. So there's all stages of stellar evolution in this picture, from pre-birth to the new birth to the older star that has already died and blown up. But if you plot a cluster of stars, because they're all at the same distance, it's essentially like their brightnesses. And so you can see the image is like this. And most of the stars in this image are along the main sequence. There's a few stars over here, and there's one little star down there. Hold on a second, I just put everybody in the middle of my screen so I can't see what I'm doing. There we go. Now, stars similar in nature based on their positions in the HR diagram. Because these stars are on the main sequence, we can surmise that those are all stars that are burning hydrogen into helium. And they're related to these stars here. And remember, we know the absolute brightnesses of stars here because we have parallaxes. So if we say, for example, the stars over here in this cluster are a lot like the stars that are right here, then they should be this intrinsically bright. So this is how bright they should be, but we observe them from Earth to be this bright. You can surmise how far away they must be. And so it's almost like shifting these stars on the y-axis until you get them to match up. Likewise, you can see the stars way up here. These stars way up here in the red are a lot like these stars here on this HR diagram. So these stars on this HR diagram are this magnitude, but we see them from Earth at this magnitude, and that difference in magnitudes tells you how far away they are. Now, why does that work exactly? Well, because we have that list of stars based on their spectral type, and we can classify them sort of like 100 watt, 40 watt, 25 watt light bulbs, and we know how light diminishes with distance. So imagine a light bulb over here, and all the light that passes through this first square, this first little window, gives you a brightness of 1. We'll use that as the calibration. And all the light beams that pass through this little window at a distance of 1 meter or 1 mile or 1 light year or whatever, then go on at twice the distance to pass through a window that's 4 times as big. So when you double the distance, you increase the amount of area here by a factor of 4. And so if you were to ask, what is the brightness of this single square compared to the brightness of this single square that's the same size, you would find out that light diminishes by 1 over the distance squared. The brightness was 1 unit when it was this far away. You go twice as far away, and now the brightness on that same area is 1/4 as bright. And so the 1 over r squared law for the diminishing of light allows us to take information we have about the intrinsic brightnesses of stars that should be 100 watt light bulbs or 40 watt light bulbs or whatever they are, and put them at the appropriate distance for how they should look, even though we see them from Earth at different brightnesses. And that's how we measure distances using what is called spectroscopic parallax. So we calibrate stars using parallax and known geometric distances. And then we utilize what we know about the stars and their spectra to understand how stars behave further away that do not have a parallax. Now, what about extragalactic distances, or distances that are so far away that maybe we don't have a spectrum, or maybe the stars are too faint and the telescopes aren't big enough to get a spectrum? The nice thing about these days is that telescopes are pretty big and can get spectra of stars in other galaxies. But in the old days, they were not that big, and we did not. So we needed some way to step out further out into the universe. This is an example of a pulsating star. One of the stars in the HR diagram where after they've had their heyday and burnt hydrogen into helium, they start to become unstable. And that instability leads to pulsation. And this is an animation of a star that is undergoing these pulsations. So like I said, they're nearing the end of their lives. They're running out of fuel in their core. And some of these stars, because of their physical characteristics, these pulsations are actually tied to their intrinsic brightnesses. So that's an example of one of these pulsating stars called a Cepheid star. And Cepheid stars are very important because they obey what is called a period luminosity relationship. Here is an example of one of these pulsating stars. This one happens to inhabit the field of view of the cataclysmic variable HV Andromeda. And these are observations from the telescope at the RRORRT at CAS. And this is days, and you can see the stars going up and down. But when you fold all those observations on the period that the star exhibits, you'll see it's got about just under half a day period. You can see that the star is brightening and dimming, just like that star I just showed you. The pulsations lead to brighter and dimmer things, and this is one of those stars. So it's very easy to do photometry of stars that are much further away and we can't get spectroscopy for. But if they're pulsating, we can measure their periods really easy. And for these particular stars, there's lots of Cepheids that we know geometric parallaxes to. And we understand that this leads to what I talked about as the period luminosity relationship for these pulsating stars. Oops, let me go back. So these are the Cepheid stars. They have a nice linear relationship. These are some related stars that are pulsators as well. They're a globular cluster rather than disk Milky Way stars, but their periods correlate with their intrinsic brightness. So again, here's how this works. We don't have a spectrum to understand what brightness the star should be, but we can measure its period and understand how bright it should be. Understand that it's a 60-watt light bulb. So then if you observe a Cepheid pulsating in a distant galaxy, you know how bright it should be, but it's very much fainter because it's in a very distant galaxy. You can use the difference in its brightness and the 1/r² law to again figure out the distance to that star and therefore the distance to that galaxy. So now we can obtain accurate distances to nearby galaxies using pulsating variable stars. This is the death of a star, a stellar explosion where the light can be seen out to truly extragalactic distances. This single star outshines nearly everything in its host galaxy. I mean, it's pretty bright. Spectroscopy helps us distinguish between two important types of supernova explosions, which is what this is, a star that's gone supernova. And those two types are from stars that are truly massive, called type 2 supernova, to stars that represent an explosion of a very compact white dwarf object. And these are called type 1 supernovae. And the difference is basically whether they're devoid of hydrogen gas or not. A white dwarf star is the stellar core remnant of a star like our sun. So at the end of its life, after it runs out of fuel, it becomes a red giant. It may pulsate, and after a while, it starts to expel its outer layers of atmosphere, and the only thing that's left is the original outer layers of hydrogen gas from its envelope and the core of the star, which is the burnout white dwarf. And you can see the white dwarf here. This is probably M57. And then here's another planetary nebula with the original star stellar gas and the white dwarf star there in the center. White dwarf stars represent the limit of compactability that is necessary to hold up a star against gravity. So the binary star Sirius has two components. Sirius B is an object with more mass than our sun, but it's compacted down to the size of the Earth. Now, because this is a binary star system, this little guy orbits around here, you can determine the masses very well, just like you can on a pendulum and a seesaw. And we know that this object has the mass of the sun, and yet it's very, very much fainter. And so this is what Sirius B actually is. It's the mass of the sun squeezed down to something the size of the Earth. And as it turns out, there's some mass limit against which this type of material can stand against the force of gravity, and it's known as the Chandrasekhar mass limit, and that is displayed here. So white dwarf stars within binary systems sometimes have mass coming from their companion that dump material down onto the white dwarf. And these type of binary systems are the types that give rise to type 1a supernovae. So when the white dwarf gains mass over time, they eventually reach the 1.4 mass limit, and boom, they explode as a type 1a supernova. That is why type 1a supernovas are very important in astronomy, because they are what is called a standard candle. And what do I mean by a standard candle? Well, a type 1a supernova is a lot like having one stick of dynamite. You always know how much you have when it goes off, and therefore it's always the same brightness when it blows up, and so they make a standard candle. A white dwarf in a binary system has the potential to gain mass from its companion, as shown in this little animation. And again, I guess this is an animation trying to show a supernova explosion or something, but anyway, you get the idea. The nice thing about supernova explosions, they are observable out to very extragalactic distances, very, very, very far. The Crab Nebula, M1, is an example of an explosion recorded by Chinese astronomers in 1054 AD. And in present time, when we pointed our telescopes to the location on the sky because they kept good records, we found this, this stuff, which is coming off at very high velocity. And if you run the movie backwards based on the velocities, you basically go back to about 1054 AD. So this is a supernova remnant from a supernova explosion in the sky. All right, so now we have distances to galaxies based on supernova. Cepheids for the nearby galaxies and supernova for very far galaxies. And now we can start using the galaxies themselves. One of the things that we notice as we look at galaxies and we take spectrum of entire galaxies, you will find that the spectrum is shifted, and that gives us a velocity shift due to the Doppler effect based on recession of galaxies. And it was Edwin Hubble who sort of understood and discovered that this shift, the further a galaxy is away, the faster it seems to be moving. And this became known as redshift. Supernova type 1a distance modulus versus observed galaxy redshift. And this is what is plotted over here on the left-hand axis. And over here on the right is sort of, the Earth is right here in the center. This is basically right ascension running around, and distances to galaxies is measured by the Sloan Digital Sky Survey, showing the structure of our nearby universe in galaxies. And you can see how it sort of looks filamentary, and there's gaps and there's clustering of galaxies based on those positions. So basically, the rungs of the distance ladder are based on this first rung. Well, actually, they're based on parallax, geometric, right? And we have some Cepheids that are close enough to have a parallax observable from the Earth, looking with our eyeballs and our thumb. Then they are calibrated based on their spectrum to understand that, yeah, those Cepheids are the same as other Cepheids in other galaxies that are pulsating at extragalactic distances. And some Cepheids in galaxies also have galaxies that have supernova go off, type 1a. So the second rung is to tie the parallax observations and spectroscopic parallax to the stars that are Cepheids and supernova in other galaxies, and then use the supernova as the third rung to go out to truly extragalactic distances. So this is sort of the 3 steps of the cosmic galactic ladder. Using the information from the Sloan Digital Sky Survey and a lot of the information from these galaxies, I found this cool animation from the Sloan Digital Sky Survey showing all the positions of the galaxies in nearby to Earth at their relative locations and precise areas. So it's sort of a oops, I goofed it up. It's sort of a fly-through of all the galaxies that are near the Earth that I just showed you in that 2-dimensional plot. It's kind of a fun little fly-through. It's what I really want my background to be for all the Zoom meetings that I attend. I want it going on in the background so that it's really cool. So utilizing, I think I'll pause there. I have a few more slides that talk about the Hubble constant, because I know Bruce is going to want to talk about that. But I thought I'd pause here and provide us an opportunity to ask some questions and do some other things. So if I can get this to pause, maybe I have to go to the next slide to do that. There we go. Does anybody have any questions?
Not I.
Not I.
Yeah, this is Doug Wilson. I have a question. Radio astronomy, this is all optical. Is there anything that would merge in or be duplicates or something in radio astronomy?
Well, yeah, in radio astronomy, they have spectral lines as well. And the same thing goes for looking at spectra in the radio region and looking at spectral lines in the radio or the ultraviolet or whatever spectrum of the electromagnetic spectrum you're looking at.
Okay, so all combined, there's actually quite a bit, and it can be done. Thanks.
Yeah. So by looking at the velocities of galaxies, this is sort of a cute little graph of the measurement of what's called the Hubble constant. The recessional velocity of a galaxy versus its distance from us gives us a number, which this number is basically a measure of the age of our universe, because if you think of galaxies receding and moving away at high speed, you just run the movie backwards until the galaxies are all at one location, and that hints at a beginning. And so this Hubble constant is a very important number in cosmology, because everybody wants to know how old the universe is. At the moment, the Hubble constant points to a universe that's about 13.5 billion years old. But this is measurements of the Hubble constant over time as we increase our theoretical understanding of the pulsation of stars, and as we increase our abilities and instrumentation to sort of hone in on the actual value of the Hubble constant by looking at distances to galaxies using supernova. And this sort of jump here at the beginning, that from way up here to down here, was basically from a fundamental misunderstanding about how Cepheid stars pulsate. So once you have that paradigm shift, you can see that since about 1960, we've got a pretty good handle on the Hubble constant. Things have been settling down quite nicely. How do I advance? There we go. This inset shows the strength of temperature variations. The graph shows the strength of temperature variations that's on the vertical, plotted against the angular sizes on the horizontal. And what they get this from is the map of the cosmic microwave background that's measured by several different satellites. But this is the inset over here of the entire 360-degree view of the night sky in the 3-degree cosmic microwave background. And you can see there's temperature fluctuations that represent fluctuations in the very early universe. So you can think about the x-axis as being basically pieces of the sky this big, and then growing up to pieces of the sky this big. So the pieces of the sky get bigger along the x-axis, and on the y-axis, those are the temperature fluctuations. How big are the temperature fluctuations within a certain region of the sky? And what you see the blue dots is data from the Planck satellite. And the red line is a cosmological model that includes estimates of dark matter and dark energy fitted to the Planck data. And so you can kind of see it has a pretty good match up until the very tiniest fluctuations, which are, way back in the early universe. So scientists will also use this as a way to understand the Hubble constant. So the first way to understand the Hubble constant is basically utilizing the Cepheids and the supernovae and the galaxy recession. So it's that cosmic distance ladder. This, the cosmic microwave background, is a second way to measure the Hubble constant in a totally different way. Recently, astronomers have been using stellar evolution and using a different way to measure the Hubble constant by using a different standard candle than Cepheids or supernova. What you see here is an HR diagram. Again, it's brightness versus spectral type or temperature. And this black line is sort of the main sequence. And this sort of represents stars of different mass on the main sequence and their evolutionary track as they would age. And most stars would age after they are done burning hydrogen into helium in their cores. They begin to expand into a red giant. And most of the evolutionary tracks end up over here in this part of the diagram. All right, so keep an eye on this little circle here in this theoretical HR diagram. And I'm going to show you a plot of an HR diagram for a cluster, which is M5. And so down here, you can see where the main sequence should be, would be along here where my cursor is going. And then all the stars above this, these more massive stars, have already evolved and are somewhere along this track. And so there's a bunch of tracks up here that end up over here that are these red giant stars, all right? And you can see that most of those stars are all similar in brightness. And so a whole lot of stars in the main sequence sort of end up in the same place at the same brightness on the HR diagram. And so these stars sort of have a standard candle, if you will. And so by looking at the brightest red giants in a cluster in a faraway galaxy, you can use those instead of supernovae to do distance determinations. And that is one of the ways in which they're determining the Hubble constant based on galaxy distances. And so this picture shows an updated version of the Hubble constant over time. Notice that it starts at about, starting at 2000. Let me get my... So starting in the year 2000, you can see the blue is the traditional cosmic distance ladder determination of the Hubble constant. And the cosmic microwave background version has sort of settled here. And then this new method using these brightest red giants. And so some of the things that you hear about, I think, Bruce, you were posting about the controversy recently, has to do with the fact that the error bars on these things have started to not overlap. And it seems to be there's a difference in the Hubble constant based on your model and the way in which you measure it. And I would say you can reconcile that by either starting with the fact that you don't quite know what's happening in terms of reddening or dust, or your model of what's going on isn't quite accounted for. And so these error bars aren't as small as you'd think they should be. And so these all three probably do agree. And until we understand adjusting the theory to these three things, we're probably going to end up with some sort of paradigm shift like we had in the 20s with the Hubble constant and using the Cepheids. There'll be this big jump. So one of these three things is going to jump based on the assumptions changing, or the starting physics that we don't quite understand changing. But anyway, that's sort of the controversy that they're talking about, is the fact that their estimates of error bars seem to indicate they don't agree. But my guess is that they'll reconcile themselves one of these days.
Jeff?
Yep.
Let me interrupt, if you don't mind, before you get too far from your
I'm pretty much
CMB,
done.
your CMB chart. I didn't
Yeah.
follow the CMB chart.
Okay.
Can you go back and explain that again?
So this upper right inset is what the Planck satellite sees by looking at the 360-degree sky. Okay.
Yeah.
And this is the cosmic microwave background. And these are deviations from the 3-degree cosmic microwave background. So say some areas of the sky are 3.001 degrees, and some areas of the sky are 2.998 degrees. Does that make sense?
Yeah, I got that now.
Okay.
All right.
So now what's plotted over here is basically the temperature fluctuation, or variations in that temperature, versus the size that you look at. Okay.
Now that's what I didn't and still don't understand. What do you mean the size that I look at?
So can you see my cursor on this screen?
Yeah.
Okay. Yeah. So let's go down. Let's just take this point right here.
All right.
What is, I got to get a video. So this is 1 degree, right? 1 degree.
Yeah.
So if you look in the sky and you make a circle of, you make a circle of 1 degree.
Okay.
Then the temperature fluctuations you see are this size. If
I
you go
see.
over here and you look at 18 degrees, then the temperature fluctuations you see are this size. If you go over here to 0.1 degree, the temperature fluctuations you see are this size. Does that help?
Yeah, gotcha.
It's a very weird graph, I will admit. And so that's what's plotted. And then by using a model of cosmology that sort of maps those temperature fluctuations in the early universe based on what we understand now about the amount and the contribution of dark matter and dark energy, they can model the observations fairly well, except at very large angular sizes. And so it's adjusting those parameters that gives you an idea for the Hubble constant. So the increased precision of the Hubble constant over time involves basically more and more points and better fitting. So you can see this very early in the 20s and whatever, or after we figured out the Cepheids pulsate, there's a very large scatter here. And so the Hubble constant wasn't known very well, but the more points we get, the more tightly and the smaller the error bars are. The cosmic microwave background comes from basically our increase in precision of measurements. So before the WMAP was COBE. COBE had an angular size field of view that was much bigger, and then the WMAP telescope allowed us to see variations that were much tinier, and now the Planck telescope has very, very tiny variations and very high resolution, and so over time, the error bars are just going to get smaller and smaller for that as our technology increases. So those are some of the videos that I had in my slide, or in my slides. And then down here at the bottom are some lab simulations that you can do on the net from Nebraska Astronomy that involve parallax, spectroscopic parallax, cluster fitting, and looking at supernova and blackbody curves. So they're kind of fun to play with, especially if you're around kids or junior high or high school students. You want to show them animations and sort of laboratory type activities. And that's sort of the cosmic distance scale in a nutshell. And I'd love to entertain any questions people have. There are no dumb questions, only me giving dumb answers.
Yeah, I've got a question about the radio stars a while ago. Their spectral lines, they're emissions, aren't they? The radio stars?
Radio can have not only emission, but absorption lines as well.
So is it there's something from the star the radio waves go through absorbs?
Yeah, there are some absorption lines in the radio region. There are absorption lines and emission lines in all parts of the electromagnetic spectrum.
Okay, thanks.
We had two great presentations tonight. And
Yeah.
how many participants do we have?
We had 19 at one point.
19. All right.
18 right now.
All right. All right. Well, thank you to our speakers. Chris, Lasley, thank you once again for doing all the work to get the Zoom to function and to make sure that everybody got on screen and muted at the right times, etc. All right. Well, let's wrap up then. Thank you, everybody. Good night.